Well, thank you very much for everyone who's here, and especially to our speakers are here for our little mini symposium. This is put on by the Thomas Young Center as part of its sort of methods interest group. And this is going to be a little mini symposium on what's it called? Predictive excitations beyond density functional theory. So it's a very broad topic, and you'll see that in the diversity of the talks that we have lined up. So, you know, excitations, as I'm sure that many people are aware, absolutely crucial to understand everything from the transport reactive, the optical properties of materials, you know, that probe these excited states of these systems, but also are fundamental for the understanding of ground state correlations and things like that. So, you know, being able to have something, a reliable tool in a theorist's toolkit for understanding these excitations is absolutely crucial. And so I'm very pleased to welcome three speakers today who are really working on emerging approaches to be able to computationally resolve these excitations. And we will start off with Marc Dvorak, who got his PhD from Colorado School of Mines, working on graphene systems, and then moved to Finland to work with Patrick Rinke, and over the course of that time has developed this quantum embedding approach that we're going to hear about today. He now has a somewhat independent position as a research fellow in Aalto University in Finland. And so thank you very much. We'll have a 30-minute talk or so. If there are questions during the talk, then please put them in the chat function, and then we'll have a kind of 5-10 minute Q&A before moving on to the next talk afterwards. So thank you very much, and Marc, take it away.
Okay. Yeah, thanks for the opportunity to present. It seems like a really good audience for this work, so that's great. Please don't let me run over time. I started my own timer here, but just interrupt if I'm going too long. So as George said, my work is about quantum embedding, and this is done with Patrick Rinke at Aalto. So I'll start by motivating embedding theories a little bit, and I'll use spectroscopy for this. Then I'll go into the theory, which is based on the Lovedan downfolding and the idea of doing this kind of renormalization of the many-body Hamiltonian in only a subspace. I'll show some results for dimers and porphyrin and outline some ongoing work to extend the theory. So the title of the symposium is Beyond Density Functional Theory for Predictive Excitations. And excitations are tightly linked to spectroscopy. And spectroscopy is actually a really good way of introducing the idea of static and dynamic correlation. So if we think about let's change my pointer. The spectral function of the single particle Green's function, we could have a spectrum like on the left or on the right. And on the left, I'm going to classify this as statically correlated. So there are many excitations close in energy, and the spectrum doesn't have a clear peak. On the right, though, there's a clear quasi-particle solution. So I would call this a dynamically correlated system. And the motivation for our work is that many systems have both types of correlation. So there can be a localized part which has this kind of static correlation, and it can be surrounded by degrees of freedom which are dynamically correlated. Wave function methods are really good at treating static correlation, because if you calculate by brute force all the eigenstates, you can compute then the exact spectrum. Green's function methods can handle static correlation, but what I really want to take advantage of is the fact that they're really good for dynamically correlated systems. I have in mind G0, W0, and these are of course a lot less expensive than wave function methods. So maybe half a step back just to make sure everything is clearly defined and we're all on the same page. So the wave functions I'm talking about are the many-body wave functions, not any kind of quasi-particle wave function or any single particle picture. If you have all the wave functions, you know everything about the system, and then you can calculate the spectrum from the layman representation. But this is very slow. So on the right is the single particle Green's function, which is very closely related to what you measure in experiment. So this could be compared to photoemission or inverse photoemission spectra. And you can directly calculate the Green's function without the wave functions. And this is usually more efficient. But of course, it depends a lot on the type of system you're interested in. So one of the challenges for the embedding is how to get these two to connect to each other, because they're different. Obviously, for one thing, the Green's function, at least the one I've written here, is the single particle Green's function. And that's a little hard to connect to the many particle wave function, but I'll show you how we do that. So the idea for the embedding is to treat the statically correlated portion of the system with a wave function theory and the dynamically correlated portion with Green's functions. So ideally, I can move the slider and interpolate between a normal exact diagonalization calculation or a normal GW calculation. Now, enforcing these limits is really important, and that's kind of the guiding principle behind the construction. But I'm most interested in this middle regime, where we actually have an embedded problem. So embedding is, of course, not new in many body physics. In quantum chemistry, the state-of-the-art embeddings are multi-configurational SCF theories, like CAS SCF. So these are nonlinear orbital optimizations in an active space. And the challenge there is to include correlation outside the active space, but this can be achieved with a PT2 correction. So that's a second order perturbation theory correction. In solid state physics, embedding is more naturally done in the Green's function language. DMFT is kind of the method of choice there, and there's a whole variety of related methods with a similar structure. And it is really a Green's function embedding instead of a wave function. And I'm not a DMFT expert, but one of the challenges is including non-local correlations. But these are rapidly being addressed with cluster extensions. So everything you see on this page is really active research. You know, the basic methods and these corrections like PT2, the extensions like cluster extensions. But we want to do something different. So briefly, embedding is good for systems in which you have a physical defect. So you look at the system, you know, in real space, and there's some kind of localized atom in a host. That's usually good for embedding. So that would be like a solid state defect. And this topic is pretty popular now because solid state defects are being researched as qubits. The other obvious choice is d electrons. So if it's a d electron atom in a molecule or a solid, the d electrons are a natural choice of active space for the embedding. And everything you see here has been studied with some kind of embedding method. And they're all either in progress or projects that I want to work on in the future with our method. Okay, so to the theory. So I'm going to start the embedding from the wave function picture, not a single particle Green's function picture. So let's start from the many body electronic Hamiltonian. So this is the standard electronic Hamiltonian, and I'll work in the basis of configurations. So we start from a reference configuration and then generate single, double, and triple excitations and so on just by permuting the orbitals. Intrinsic to any kind of embedding is a partitioning of the problem. So for this, I'm going to partition the Hilbert space. Now this is still the many body Hilbert space. To connect to the single particle picture, I'll define an orbital active space. And all the excitations I can create in the orbital active space define a set of configurations that I label D. So this is generated the way you would generate the active space for a complete active space theory. And then all the other configurations I label R, and I'll call this the bath space as opposed to the active space. And transitions which go from the active type to inactive, I put in R. So these are bath configurations. Now in reality, I've separated all the configurations. In practice, I'll keep only the bath configurations, which are single or double excitations from the active space. So the basis is generated the way that it is done in multi-reference CI singles doubles, if you know what that means. If you don't know, it doesn't matter. It's not so important. So now the downfolding. So I'll downfold the many-body Hamiltonian with the Loveman method. So DNR are subspaces, but they're also projection operators. And I can rewrite the Schrodinger equation in block form like this. And it's a little bit of algebra. It's straightforward to work through on your own. You basically solve for this, the second part of the wave function and insert it into the first line of the equation. And what you get in the end is now an embedded Hamiltonian. So I've downfolded the full many-body Hamiltonian into the active space. So the Hamiltonian itself is now much, much smaller, but it's energy dependent. So E here is the eigenvalue that has to be found self-consistently. So this is a nice trick. It's embedded, but it is still a very expensive problem to solve. And if we look at it graphically, there is this red block of the Hamiltonian, and that enters in the resolvent. It's very, very large. So to give you some estimate of the size of these blocks, this blue block, which is the size of the final Hamiltonian, is maybe 1,000 determinants. The red block is, I don't know, could be 1 million up to 1 billion for the systems that I've been looking at. So what I've done now is stuff all the expense into this red part of the Hamiltonian and its inversion. So actually I have done nothing yet to reduce the cost. I've just embedded the problem. Okay, so now we're going to start to get to something more interesting. As I said, the resolvent requires inverting this huge block of the Hamiltonian. So let's imagine we can write this in a diagonal form, where on the diagonal are all these total energies. These are not actual total energies, but let's pretend we've diagonalized this block and we write it in this form. So what I want to do is subtract an energy from the diagonal. Now, this is kind of a trivial decomposition of the matrix because I can just remove some energy from the diagonal. But I'm going to give this physical meaning because I know that if this was the full Hamiltonian, this decomposition would be the ground state energy plus excitation energies. And I want to use that same idea. So instead of working on the left side, which is kind of the many-body wave function picture, I want to work on the right side. And I'm going to compute this E0R and these omegas, which are excitation energies, separately. And to construct this, I'm going to take advantage of the limits because I know that in a certain limit, I should get back the full excitation energies in ground state. And the other limit is basically the Hartree-Fock limit. So I should get Hartree-Fock particles. So this is the idea of the theory, not just the embedding, but actually the theory behind what we're doing. So I want to perform this quasi-particle renormalization in only the high energy subspace on just a block of the Hamiltonian. And the reason is that we're really good at using Green's functions to calculate excitations. So I want to do these separately and calculate E0R and omega R separately. And hopefully it will be less expensive than actually diagonalizing this block of the Hamiltonian. So this is the key where I flip the picture from the wave function to the Green's function picture. Now I've set up the embedding where I need to choose the subspaces so that this bath space R is the dynamically correlated space where the Green's function methods will work well, at least the Green's function methods I want to use. Okay, to connect to the determinant basis, we can't use just we're using now, I'm interested in the optical problem. So I can't use the electron hole Green's function. I have to allow for multi-particle excitations because the configurations can take any excitation level. So here again, we have single, double, and triple excitations. If I really wanted to be formal with this, these would be n-particle Green's functions in the subspace. Now, I'm not going to deal with these formally. What I'm going to say immediately is that the n particle Green's function can be decomposed into n single particle Green's functions. So this is the first level of approximation I could use, which is that I have let's say I have a double excitation, I have 2 propagating electrons and 2 propagating holes. To make this a better approximation, now I'm going to give each one a self-energy. So this means that instead of having Hartree-Fock particles, I now have GW quasi-particles, and I'm going to use the GW approximation. Now, to avoid double counting correlation, I have to employ some constraints because I don't want any correlation on these bath quasi-particles with the D subspace. That's the active space, and that will be solved later. So to avoid double counting correlation, I use the constrained random phase approximation. So everywhere in the perturbation expansion where the Coulomb interaction enters, I'm going to use the constrained polarizability. And this is already really well known and applied extensively in DMFT and related methods. So basically only the R excitations can screen the interaction. And this will again satisfy the limits of the embedding, because if the R space becomes the entire Hilbert space, I get the full interaction back. And if it shrinks, then I get no screening. So the final step in improving this excitation energy is letting the quasi-particles interact with each other. So this is like going from a GW calculation to a beta saltpeter calculation, where we now let the electron and hole interact with each other. So what is written here is the final way I calculate these excitation energies. And it's actually very easy to understand if I go through it piece by piece. So there's a one body part where each electron or hole has a self-energy. So there's quasi-electrons and quasi-holes. Then there's an electron-hole interaction, an electron-electron interaction, and a hole-hole interaction. And all of these quasi-particles interact with the partially screened Coulomb interaction. So diagrammatically, this level of development looks like this. I go from Hartree-Fock particles to quasi-particles to interacting quasi-particles. And I'm going to take now from the denominator of this n particle Green's function, the renormalized Hamiltonian. So now that I have this excitation energy part, I'm going to insert it into the resolvent in place of this projected block of the Hamiltonian. So the final equations look like this. It's a complete active space theory for the static correlation, and this active space wave function is embedded in a bath of interacting quasi-particles. And actually, up to this point, I haven't done anything to reduce the cost of the problem. It still is very expensive, but I'm going to make a diagonal approximation so that this very, very large matrix inversion and multiplication is now reduced to a diagonal. So to give you some idea of the size of this, the active space produces about 100 to 10,000 determinants, and the sum over the bath configurations can be from 1 million to 1 billion, at least for the systems I've studied so far. Now, even in the diagonal approximation, these bath states are still correlated. All the particles have a self-energy and they interact with each other. So it's a pretty straightforward build, diagonalize, iterate type of procedure. I've built this now into FHI Ames. CSC is our supercomputing center here in Finland, but the procedure goes from Hartree-Fock to GW to DCI. It builds on the previous development in Ames for all this, and the code is parallelized over computing the matrix elements. That's where all the expense is. Okay, results. The first test for these methods is dimer dissociation. So dimer dissociation is a really non-local problem. If you have any kind of single reference theory or mean field theory, it will struggle in the dissociation region. And also at dissociation, sorry, it will struggle in bond breaking. And at dissociation, the correct wave function is not a single Slater determinant. So this is a really difficult test. It's a favorite of quantum chemistry. So we applied DCI to nitrogen dissociation. The active space is the triple bond. So it's a 6-level active space. And the DCI results are in red. And the most important thing here is to point out that there's no maximum in the dissociation curve. And that dissociation, the DCI curve is flat. So the results are good in that sense. Also, the excitation energies look really nice. The theory is naturally suited to excited states. It's state dependent, so you have to iterate on each state individually. But it's not. Excited states are naturally included. So one thing worth pointing out on the right side is this conical intersection. The dashed line is reference data, reference theoretical data that was in a different basis set. So that explains the large vertical shift. But our results are the solid green and magenta lines, and they capture this conical intersection. So this shows that we are getting the static correlation correct. It also is a good indicator that the subspace we chose is good. O2 is another dimer to dissociate. O2 is a little different. It has a triplet ground state and then 2 low-lying singlet excited states. Yeah, my results are here. The results are pretty good, in pretty good agreement with experiment. I can also compute ionization spectra. So if I remove an electron, I get all of the n-1 or n+1 total energies, and then I can compute excitation energies. So we tested this for benzene. So this is the particle removal spectrum for benzene. And our results are again shown in red. The agreement with equation of motion coupled cluster singles doubles is pretty good. This peak in benzene is a bit stubborn. This is a problem we want to return to find this sigma peak here. Hopefully we can improve upon our results that I'm showing here. But overall, the agreement is pretty good. There can also be other effects that affect the experimental spectrum, like vibrations. So the largest system I've studied so far is porphyrin. This molecule on the top right is magnesium porphyrin, which just means there's a magnesium atom in the center. So porphyrin is well described by a 4-level model attributed to Guterman, and it is these 4 lowest levels here. So this is the VBM, I'm sure I'll say this wrong, the VBM -1, the CBM, and the CBM +1. So the 4 frontier orbitals. And by symmetry considerations, the lowest excitations should be these QX and QY excitations. And QX mixes these 2 single particle transitions like this, and QY mixes the other 2 single particle transitions. So this is a really nice active space. And the other great thing about porphyrins is that you can place a d electron atom in the center. And that's also really well suited to an embedding theory. So for this system, we did a 4-4 active space, 4 electrons in 4 levels. And it's embedded in about 400 orbitals in the bath space. So that gives a number of bath determinants of about 1 billion. So this is a pretty large, this is the largest calculation I've done so far. So free-base porphyrin is just the porphyrin molecule without an atom in the center. It's just passivated there. And my results are shown in blue. So this is the convergence curve as I add bath orbitals. A really nice comparison here is to the red curve. So this approximation I call diagonal H, and that is instead of using the diagonal excitation energies the way I described them, I just use the diagonal many-body Hamiltonian. So it's the bare Hamiltonian with no screening. So by comparing the red and the blue curve, I can actually isolate the effect of the screening in R. So this enters in the in the self energy that each quasi-particle has, and also in the screened interaction. So for porphyrin, this difference is 0.78 eV, which is pretty substantial. On the right, you can see how the result compares to some quite expensive quantum chemistry methods. These are active space methods from quantum chemistry. And the result is pretty good. This was the first excitation in porphyrin, which is QX. QY shows a pretty similar behavior. Actually, the convergence is different. There's a kind of a local maximum in the convergence of the QX curve, but not for QI. But the result is in good agreement with experiment once again. And the DCI calculation is relatively inexpensive compared to these active space methods from quantum chemistry. And we still get good results. So magnesium porphyrin is the final porphyrin I've tested. No d electrons yet, but the results are pretty good. Again, compared to much of the same, well, data from many of the same references. However, there is a small problem with the porphyrin calculations. And that is that the singlet triplet splitting is very small. It practically vanishes. So for free-base porphyrin, using the data that I've shown you already, the singlet triplet gap is only 70 milli-electron volts, which is too small. This is not really physical. So the solution to this is to use a block diagonal approximation. So instead of having just a diagonal here in the resolvent, I'm now using blocks and inverting small blocks. So the blocks are diagonal in the band index or the spatial orbital index, but then I construct the block in the spin subspace of those orbitals. So basically now I can construct proper triplet or multiplet blocks and do the inversion this way. And the good thing is that this fixes the singlet triplet gap. So on this slide, you can compare the two red numbers to each other. So that is an experimental number for the QX excitation and a DCI calculation using the block inversion. Now you can do the same thing for the purple numbers here. Those are the experiment and the block DCI triplet values. On the right side, I've summarized the results in a table. So before, the singlet triplet gap with DCI was 0.07, and now it is 0.69, which is much more physical. That's a number that you would at least expect. Experimentally, it's measured at 0.44. So it's improved. However, the singlet excitations now are not in as good of agreement as before. So now we're working on some theoretical extensions to hopefully improve this. So a common feature of embedding theories is feedback from the impurity or the active space to the bath. So this means that, okay, I've set up my impurity problem or my active space Hamiltonian, and I get a really good result here. From it, I somehow need to put this result back into the bath space. The interesting thing is that if you look just at the Lovedan partitioning, there's not any feedback like this. The only feedback is through the eigenvalue E. So the problem is energy dependent, but there's nothing, basically there's not a Green's function here. If you have in mind Green's function embedding, the only feedback is the eigenvalue. So we're working on how to get this feedback into the theory. It might still be possible. There are 3 ideas on how to do this. The first one is to update the active space orbitals. So we start with an initial choice of orbitals in active space. And then based on some numerical criteria, I can update the active space, rotate the orbitals, and keep going until I have some kind of idealized active space for the system and get a good result. And this needs to be formulated sort of numerically. So we don't just get a good result, but somehow we get a result that's kind of numerically consistent. So that's the first strategy. And now there's feedback from the impurity to the bath because, well, the impurity is changing. The second idea is to implement some kind of constrained self-consistency within the bath space. So everything I've shown you was done with G0W0 because that's really efficient and we're really good at it. But an idea is to take the perturbation expansion in the bath space to infinite order. Instead of stopping at G0, W0, I can iterate this. Of course, self-consistent implementations of GW exist, and the theory for self-consistent GW is there. The interesting thing is that in the subspace, we're not working with the self-energy of the full system. And similarly, I wouldn't construct the full Green's function this way because I have to follow the partitioning and I can't mix in anything from the D subspace. So that's an advantage. It follows the Hilbert space partitioning exactly. So the idea here is to first do a self-consistent calculation in R based on the single particle Green's function. And then I basically, again, take the quasi-particle solutions from that result and insert it into the resolvent. And then do the DCI calculation this way. I like this one personally because it's really consistent with the embedding. We can do essentially whatever we want in the R space, use something beyond GW, do self-consistency as long as we constrain the calculation to that subspace. The final idea is most similar to a Green's function embedding theory. So can we use a full updated Green's function to update the bath space? So let's say I do a single shot DCI calculation exactly the way I described. So now I have really good wave functions and excitation energies in the active space. I can update the single particle Green's function because I can now calculate really good self energies in the active space. So let's say I start with a GW Green's function. I insert the self energy I calculate with DCI, and at the same time remove the original GW self energy. So this gives me now a really good total Green's function. Now, to get into the subspace, I need to remove the effect of the active space because I have to follow the Lovedan partitioning. So to me, this is a more complicated way, at least this part that I'm describing here, of reaching the same result as the previous slide. I can't use the total Green's function in the bath space. I have to use this kind of GR thing that I've labeled. So roughly how this could look, I start with a DCI calculation, just as I've described in the previous slides. From this total result, I can calculate an improved full single particle Green's function because I can calculate a very good active space excitation energies and wave functions and self energy. This somehow gets fed back into the bath space and is incorporated into the excitation energies there. And this entire procedure now is then iterated until self-consistent. So it's an idea. It's not totally formulated yet. So in conclusion, DCI balances static and dynamic correlation. It really plays to the strengths of these two approaches, which are wave functions and Green's functions, especially perturbative G0, W0. And it's feasible for large systems. I've now done a 4-level active space embedded in 400 bath orbitals. It's state dependent, so it's really good for excited states. And it passes the multi-reference tests we have posed so far. And theoretical extensions are in progress. So with that, I'll conclude and take any questions.
Thank you very much, Marc. So does anyone have any questions? If they do, feel free to raise your hand or post a question in the chat. I might just kick things off very quickly, just while people are writing questions. A naive question that I clearly just missed. I kind of have certainly got at least the kind of qualitative understanding about how the downfolding is done from the GW in the environment. You're still left, obviously, at the end of the day with an energy dependent problem in your active space that you need to solve.
Yeah.
How do you solve that exactly? Is that solved as you would a kind of Dyson equation where you have to iterate the energy along with the solution?
Yes.
Right.
So
Okay.
I just iterate on the eigenvalue.
Right. Okay.
Maybe someday I'll simplify this. I could linearize it or something.
Mm.
But for now,
That's
I
what I was
just
thinking.
iterate it exactly. Yeah.
Okay, that makes sense. And then the active space itself, at the moment, are you constrained that your active space has to essentially be sort of canonical mean field orbitals?
Yeah. So this kind of goes in line with the first strategy I proposed, which is updating and improving the active space.
Mm-hmm.
I think if I'm just using diagonal G0W0, I am constrained.
Mm-hmm.
But I think there's no reason why I can't rotate into any basis I want. It should be possible.
Okay.
It will take some more work.
Sure. Okay, thanks a lot. Okay, so in the chat, we have a question from Johannes Lischner, who says, there's been some work by Philipp Werner on in the context of DMFT that casts doubt on the accuracy of CRPA. This makes me wonder how sensitive your results are on the choice and the size of the active space.
Yeah, good question. I have grown the active space for porphyrin and for benzene, and it's relatively insensitive. Now, it grows, of course, the expense grows exponentially, so I can't grow it dramatically, right? But it's relatively insensitive. CRPA, yeah.
Yeah, I mean, I might just add to that. If I understand what's being done here, most people, when they're using CRPA, essentially find the constrained screened Coulomb interaction and then take a static limit,
right?
By setting essentially omega equal to 0, and then that's your effective Hamiltonian. On the other hand, I guess you're including the dynamics of all of that effective screened Coulomb interaction in your bath space through the energy dependence of your effective model. So in that way, it's maybe slightly different to CRPA.
Yeah, it's different. I mean, it's, I still have a hard time wrapping my head around it. So what happens is that the entire Hamiltonian, in my case, is renormalized at once. So, I mean, the entire active space is renormalized at once. That's 2-body and 1-body parts. So, for example, if you were to take just the CRPA screened Coulomb interaction and take the static limit, I think ordinarily people will use this as the 2-body part of their renormalized Hamiltonian. But actually, the way that I do this, it also affects the 1-body part. So it's just not, it's hard to line them up exactly. It is a little bit different.
Yeah. And presumably from the dynamics, you've actually got effective higher order contributions as well from the RPA.
Yeah.
Excellent. Okay, are there any more questions? I see Philipp's raised a hand. Go for it. Oh, I'm not sure we can hear you, Philipp, or maybe it's just me.
No, I don't hear anything.
Is this better?
That is better. It's a bit echoey, but it'll do.
Okay, let me see here. Yeah.
Oh, we just lost you somehow?
Yeah.
Okay.
Maybe you should take another question first while I figure this out.
This all bodes very well for Philipp's talk later on.
Yeah. It's the echo cancellation that's snagging me. Here we go, I think.
Yeah, I think that's reasonable.
You could type it as well.
So how is this? Can you hear me?
Yeah, that sounds okay.
Is this audible?
Sounds good.
Yes.
Great, except that I can't hear you now, but we'll figure it out. So I was just wondering about these CAS PT2 results for porphyrin.
Okay.
I thought, you know, for the Q band, you had a relatively large deviation in the difference to the experimental value. I think it was 0.5 eV or so.
Okay. Let's bring it up.
That seems really large.
Oh, dang it. So you said the QX or which one? Either one.
Yeah, here. The QX was even worse.
Yeah. The theoretical data I have found for these molecules is really scattered. It is a little bit surprising. Off the top of my head, I don't know the size of the active space they used. It was surely not 4.4. It was larger than that.
Sorry, no, I can't hear you.
Oh. Can you hear me now?
Hello, Philip?
Yes, now I can hear you.
Okay.
Okay. So for QX, the theoretical data is pretty scattered for this. I was also fairly surprised.
So could this be vibrational effect or?
It could be. Yeah, I don't know. So this, I can tell you the largest active space was this CAS SCF MC. That's kind of my own abbreviation. It's this Monte Carlo based CAS SCF calculation. And it was maybe something like 34 orbitals for the active space, I want to say.
Right, but this is like, okay, yeah.
But I don't have a great explanation. The theory is pretty scattered.
Right, I think the thing that worries me a bit is this big difference between the PT2 results and, you know, the experiment. So that doesn't, you know, I mean, that's more than you, I don't know, TDDFT is as good almost, I think,
yeah,
for this transition, right?
Yeah, I think it is.
Yeah, wasn't it so that also beta salpeter does fairly well here? So this is actually not such a correlated system unless you put a d-electron system in. So that might explain actually why the pure active space methods are doing far worse here than the BSE-based, so Green's function-based ones, right? And our addition now where we tack on the active space to a Green's function one.
So to be fair to these authors in this paper, the purpose of this paper was to highlight the CAS SCF MC results. Okay, it does all come from the same reference, but yeah, so the paper was meant to highlight the CAS SCF MC.
Okay, fantastic. Well, thank you again very much, Marc, for the talk. I think it's probably time to move on,
Sure.
But we can, if there are any further questions, do feel free to put them into the chat. And if you could unshare, then you can share her slides. Fantastic.
Okay, great. Should I just
Thank you.
Oh.
Well, I'll give you a little introduction first to make sure everyone knows who you are. So the next speaker will be Neepa Maitra from Rutgers University in New Jersey, and Neepa works on a whole variety of things from TDDFT coupling to nuclear motion, polaritonic chemistry, and as well actually on the development of embedded approaches for electronic structure as well. But today she's going to be talking about TDDFT for photoexcited dynamics. So thank you very much.
Mm-hmm. Well, yeah, thanks a lot, George. And yeah, as so I'm going to center the talk on photoexcited dynamics, but in particular, the TDDFT description of the electronic system after some kind of excitation. So I won't be talking so much about the electron-nuclear coupling side here. Okay, but yeah, so actually for dynamics, for photo-induced dynamics, TDDFT has had some great successes. It's been used for a range of different applications, from photovoltaic design to watching the density move after a ionization event and things like this. So, and in all these situations, either the electronic system has been left in some kind of superposition state, which drives the dynamics, or the ionic motion drives the dynamics, or there may be a field applied, right? But in these cases, it's yielded some useful agreement with experiment, to the point that one can sort of point to different mechanisms undergoing the different phenomena that's observed. So I won't go into that too much here. I just want to note that there are also some failures, and this is more what the talk will be about, actually. But I'm going to, and kind of how to get around these failures. But for example, this is actually an older paper by now, but it hasn't, a good method hasn't actually been resolved yet for this kind of problem. So it's this lithium cyanide molecule that was studied in Matthias Nest's group, where pi pulse drives an electron from the ground state to an excited state, which has a charge transfer character. And if you look at the dipole moments through the evolution, you can see that there's a dipole switching. So the idea is, can we develop and simulate switches, molecular switches in this way, or dipole switches? And so, the wave function methods, the CI singles doubles, show this large change in the dipole as the electron moves over. But if you look at, for example, LDA, PBE, or Hartree-Fock, they completely fail. And in fact, you can actually model this dynamics with a very simple system, which is 2 electrons in 1D, and where you start with the 2 electrons in a double well, and you resonantly drive 1 electron to the other well. And you see a very similar kind of switch. In the exact dynamics, which is the black here, you see this dipole with a large change, right, like this. But now with these DFT approximations, which are non-local in space, the self-interaction corrected LDA and exact exchange, you find that they begin to mimic quite well, but then ultimately fail. And what's interesting here is if you look at the excitation energies of these approximations predicted by these approximations for the charge transfer excited state, they're not bad actually. They're non-local enough to actually get pretty good agreement with the exact. But despite giving accurate excitation energies, the same functional approximation fails to give good dynamics. So this kind of raises the question, if a given functional approximation is giving much larger errors in the fully non-perturbative regime than in linear response, is there a way to kind of formulate the problem in certain situations where you can actually extract information about the fully non-perturbative dynamics from the linear response regime? And so this is, I'm going to show kind of 2 cases where, which show this in practice, right? And one is involving electron atom scattering, which we studied with a real-time, time-resolved approach. And then also these scattering probabilities can be extracted also with a response approach. And the other is Ehrenfest dynamics, which also can be reformulated in both ways. And again, so maybe I'll begin first by reminding ourselves what the equations are in the TDDFT and memory dependence, which is kind of behind the failures in this fully non-perturbative regime. Okay, so in time-dependent DFT, we evolve these single particle time-dependent Cohen-Sham equations, where the one-body potential is written as a sum of 3 terms, like in the ground state case: the external potential, a Hartree interaction, and the exchange correlation potential, in which also the many body effects of the true system are hiding in a kind of one body way, right? These are all single particle equations, right? And the idea is that if you take the density of the system by summing the orbitals squared, you actually, in principle, get the exact density of the interacting system if you had the exact exchange correlation potential, which of course we don't, right? So you might think, well, this looks like ground state DFT, of course, but of course it looks a little different already at this stage without any details because of these extra functional dependencies. And so we see here that we see here that the exchange correlation potential depends on the initial interacting state of the true system, and also on the initial cone-sham choice of orbitals or slated determinant or not slated determinant that we decide to actually begin our evolution in. We usually choose a slated determinant, but we don't have to, right? So this is an initial state dependence that arises because the one-to-one mapping between densities and potentials in TDDFT depends on the initial state. It's only one-to-one for a fixed initial state, in other words. So the potentials in the theory depend on the choice of the on the initial states here. There's also another source of memory, so we call that initial state dependence memory, but there's another source of memory in that the potential at time t depends not just on the density at time t, but on its entire history. Okay, and so, yeah, but again, if we have this exactly, if somehow we knew this, we would get the exact results of the interacting system, and of course we don't have it exactly, and I'll get back to in a minute to how we approximate this usually in calculations. Of course, in TDDFT, the vast majority of applications are for spectroscopy, excitations and spectra, as was the subject of the last talk, actually. But in there, instead, we have a simpler functional, in a sense, to deal with, because we just need to look at perturbations around the ground state. And then actually you get a set of equations, a Dyson-like equations, which maps response functions of the interacting to the non-interacting system through this exchange correlation kernel, which is the functional derivative of this with respect to the exchange correlation potential with respect to the density evaluated at the ground state. And the point is that if you now, this is usually done in the frequency domain, and memory then endows this with a frequency dependence because of the dependence of VXC at T1 on densities at earlier time T2, right? So it's not just a delta function, and this ends up giving a frequency dependence to the kernel. Okay, so how do we treat these in practice? Well, you usually select an approximation from ground state DFT and simply plug in the instantaneous density. So you're completely neglecting the memory, right? And these are called adiabatic because they're sort of an implicit assumption that the exchange correlation effects of the system is as if it was in a ground state. It's the same as if it was in a ground state, right? And so if it was in a ground state at every given time, then there would be no problem with this approximation, right? But of course it isn't. So this is how we might schematically represent that. It's just the functional derivative of the exchange correlation energy with respect to the density evaluated at the instantaneous density as we evolve. And of course there's the adiabatic LDA, the simplest approximation, if you like, where you just use the uniform electron gas to generate the exchange correlation potential, and you take its functional derivative, and this is not only completely local in time, right, but also completely local in space. Okay. Now, we can see that errors are arising in such approximations from two sources. One is from the choice of the ground state functional approximation, and the other is from actually making the adiabatic approximation itself. So in cases where we can access the exact ground state functional, it's very useful to look at what's called the adiabatically exact functional or potential, where you insert the time instantaneous density into the exact ground state exchange correlation potential. And so this here would isolate effects due to simply memory. Okay, so what about the exact exchange correlation functional? So I mentioned that, in principle it has memory dependence, and in the linear response regime, this introduces frequency dependence, as I explained, and this is needed if you want to get certain excitations, like double excitations. But in the non-perturbative regime, a consequence of this memory dependence is that you end up sort of generically in any kind of dynamics, really getting these sort of dynamical step and peak features in VXC. And I'll show you a couple examples of this. But in developing sort of, we've also tried to sort of develop practical, general non-adiabatic functional approximations, which actually turned out to be very difficult. And with a former postdoc, Lionel Lacombe, he made a very heroic effort to implement a new approach to the problem, coupling it with a density matrix approach. And he was able to capture these steps and peaks, non-adiabatic effects, but the system, it wasn't a practical approach because after very short times, the method became unstable. So as of now, we are still searching, and it's a difficult problem to capture these. So let me just make this a little bit more definite by showing you what I mean by these steps and peaks. So if we like, we could look at, to get exact results, we take a 1D 2-electron system, 1D helium, and we start in a superposition of the ground and first excited states and evolve in time. And so not surprisingly, the density just oscillates with and that's the black here, the density oscillates with a time, a frequency dependent on the energy difference of these two states. And you can see what I've plotted here also is the exact exchange density. And, you know, it kind of oscillates too, but not quite. It doesn't actually have the same, it doesn't even have the same a single frequency. It's got several frequencies. The dynamics is clearly different. And if you look at the potentials, they're completely different. The exact exchange in purple is completely missing these large steps and peaks that we see in the exact. And in fact, these features cannot be captured by even the best adiabatic approximation. In other words, any ground state, the exact ground state approximation used in this adiabatic way. And just to show you briefly how this looks, this is the red here, the adiabatically exact, in each picture, the potential, and the light blue is the ALDA. And the black dashed here is the density at different time steps, but and the black is the solid. The solid black is the exact potential, and there's very little resemblance between the black and the red, as you can see. Okay, we might think, well, you know, is this a consequence of 1D? I mean, come on, you're looking at this toy system. Well, so Davud Dar, a PhD student, managed to make another heroic effort to actually invert and find the exact time-dependent cone-sham potential for a real system, the analogous dynamics in the helium atom, the true 3D helium atom. And we took a superposition state of the ground and the 1p state, the 2p excited state, the lowest accessible state. And we find these plot sections of this potential. Again, we see these large step features which evolve over time. And they're just as large, if not larger, at certain angles. Of course, it's a 3D problem. And you know, this required sort of solving for a Sturm-Liouville type solution, solving a Sturm-Liouville type problem for the phase, and then inverting to find the cone-sham potential. You can see the details in this paper here. Okay, but going back now to this problem. Okay, so we're going to still kind of think about these steps and peaks, but let's ask a different question. Well, you know, are there some dynamics for which we can kind of get non-perturbative behavior, if you like, right? And but looking in the response regime. So maybe let me show you another example, which is that of electron-hydrogen scattering. And here we go back to our 1D model, and we have an electron scattering off a hydrogen atom, and the black is the density. So you can see it approached it interacted, it exchanged some energy with the electron and the hydrogen atom, and then reflects back. And if I look at the density, then if I take like the number of electron density and integrate it from like -5 to the right, I define therefore a reflection coefficient, if you like, and you can see that, or the number of electrons reflected, and you can see that there's this reflection coming up here. These are the approximations, ALDA, adiabatic exact exchange, and you see in the red and the blue, and you see that they really do a very poor job in capturing any reflection. This is inelastic scattering. There was a lot of energy exchange with the hydrogen atom sitting there. We can also look at elastic scattering, so lower momentum. And you find also that there's quite an underestimate sort of the reflection in this case. Okay, there's a detail to do with the initial states, which I don't think I have time to go through here. I can return to it if you're interested. What cone sham initial state did we use? I'll come back to that if you're interested. I'll also skip this for now. But then we ask ourselves, we remember that from sort of undergraduate, that when we did scattering, and maybe our undergraduate quantum class, we looked at, these 1D problems where you looked at transmission reflection coefficients, right? And this was in a time-independent framework, right? We looked at solutions of time-independent Schrödinger equations. So you can get scattering probabilities from time-independent quantum mechanics. And so this motivated some earlier work of Kieran Burke and Meta van Vassen and Adam Wasserman and co-workers, where they said, well, we could, for elastic scattering at least, we can take an n+1 electron system. So the target has n electrons and you add 1 electron. Then we solve for excited or continuum states of the n+1 electron system, and from that we can extract T and R, or scattering phase shifts in the fully 3D case. We won't get a time-resolved picture, but if we just want to know kind of the steady state reflected probability at the end of the day, this should work, right? And so they showed here how an efficient way to get this with linear response TDDFT, where essentially you can also, instead of having to actually explicitly deal with continuum states, you put your system in a box which is big enough that outside the box, the particles, the potential is essentially just a Coulombic, like asymptotic decay, or asymptotic Coulombic, or flat, meaning that we know the behavior of the wave functions outside the box. Here's the box here, and the point is that moving the wall of the box then it will coincide with the nodes of different continuum eigenfunctions, so different energies. And so actually by solving, and inside the box for a given box size, the solution of Schrödinger's equation is the same as for the continuum case. And this actually idea goes back to Ugo Fano, in fact, in the 1930s. So it's a kind of a clever way to get phase shifts, scattering phase shifts from, bound, box boundary conditions, if you like, right? But anyway, they were able to look at this and derive an expression for reflection coefficient, transmission coefficient, or scattering phase shifts in terms of the energy. And so we actually looked at this for our 1D electron hydrogen scattering problem, and did something similar, adapted it for 1D, and we found that from linear response, the reflection coefficient given by adiabatic exact exchange is 0.494, while the exact was 0.45. Well, it's not that bad. While from the real-time calculation, and this is for, again, elastic scattering, and if I plot the NR, that's the black dashed here, it's this here for the exact, and then the approximations, the ALDA is in red and the adiabatic exact is in blue, is the blue here, and you see it's a very poor underestimate. So this is, again, this point that actually we have the same functional, the same observable, but we have two completely different answers, right? And one obviously is more accurate. And why is it more accurate? Well, we're going back to this idea that the accuracy depends on, the domain of the functional. We're using an adiabatic functional, right, which is built from the ground state. So clearly it should be more accurate for problems like ground state, and also for perturbations around the ground state, rather than sort of a real-time problem, time-resolved problem, where you're actually you're getting the density. You're having to evaluate this on a very non-equilibrium density, nowhere near a ground state, right? And this is why this is so poor. The real-time calculation is so poor, but the linear response result is accurate. Again, you can only do this for elastic scattering, and you can only really get final steady state values because we don't get the time resolved picture. Okay, so I'm not sure how much time I have left, but maybe the last few, actually, how much time do I have left?
Let's go for 5 minutes or so.
Okay, yeah, so that's probably okay. Yeah, so now turning to this last part. So we'd like to now see, okay, another place where actually we have a choice of where, which formulation to use is with Ehrenfest dynamics. So now we're going to couple our electronic system to nuclear dynamics. And so in Ehrenfest dynamics, which is one of the simplest ways to do the coupling, it's very approximate, but it gives you a mean field force on the nuclei. And this is obtained in this way. So if you look at the Heisenberg equation for the nuclear coordinate, you just get, minus the gradient of the Born-Oppenheimer Hamiltonian. But if you then equate that to its expectation value, that essentially defines the Ehrenfest dynamics. So each nuclear coordinate, in Ehrenfest dynamics, you usually run an ensemble of nuclear trajectories, and each of which is correlated, or associated, I should say, with an electronic state. So psi here is the n-electron state, many-body state. I here is labeling the classical nuclear trajectory in our ensemble, and this is the gradient of the Born-Oppenheimer approximation. So when we do this with TDDFT, of course, we don't have access to the full interacting wave function, but we have two choices. We can either simply realize that the gradient here involves only one-body operators, because the electron interaction doesn't involve any nuclear coordinates. So it's only the electron-nuclear interaction and the nuclear-nuclear interaction that comes in here. And because it's only one-body operators, here, then the expectation value is very easy. It's just given by the electronic density. So you get this equation for the nuclear force, and then you'd have to solve alongside to get the electronic density. You'd solve the one-body time-dependent Schrödinger Kohn-Sham equations, and with an approximation for VXC. So this we call real-time Ehrenfest, and you'd have to solve time-dependent Kohn-Sham equations for n of r of t. All right, so you'd have to have an approximation for this. But another formulation is where you'd take your many-body state and make an expansion in terms of Born-Oppenheimer states for each nuclear configuration at each time. And then if you plug this into this equation here, right, just simply sticking it in here and then doing the math, you get this weighted force term, and then you get these couplings which depend on the non-adiabatic coupling between two electronic states. And you get an equation for the electronic coefficients. And this is very interesting because, in fact, if you look at what's needed here, all of what's needed, it can be accessible from linear response TDDFT. The energies and the non-adiabatic couplings, at least between the ground and first excited state, is accessible from linear response TDDFT. For quadratic, for the between excited states, you'd need to go to quadratic response, and there are some issues there I won't get into here. But in principle, like if you had an approximation for those, and the formulation suggests you can get all of these quantities. You can do, instead of doing real-time TDDFT, you can actually get Ehrenfest dynamics using linear response. And in fact, one might then say, does it matter which way to do it? In fact, in different codes, it's coded differently. CPMD, for example, does Ehrenfest in this linear response way, whereas Octopus or Quantum Espresso look at the real-time way. So here are the equations again. And so, of course, if you had exact functionals, you would get identical results, but not with approximate functionals. And I guess you know now that which one you'd want to pick, right? This here, you need the functional on a fully non-equilibrium domain. Here you need the functional on domains close to the ground state, right? You just need these perturbative quantities, ground state and FXC. And so, the idea is that linear response Ehrenfest is expected to be generally more accurate than the real time with currently available approximations. So we actually then went ahead and tested this on a model. I'll just summarize quickly what's in the model. It's a 2-electron and 1 nuclear coordinate system. The ground state as a function of the Born-Oppenheimer, as a function of the nuclear coordinate looks like this, the electronic ground state, while in the first excited state at large r, there's a charge transfer character. And if we look at the potential energy surfaces with ALDA, adiabatic exact exchange, we see that the ground, and the black here dashed is the exact, we see that they're pretty well approximated. There's some deviation here in the middle where there's some charge transfer character starting to build in, which is not well reproduced actually, not just charge transfer effects actually. In the large range limit, in fact, you get the adiabatic exact exchange gets this charge transfer character while ALDA doesn't. And we're going to begin, if you begin here, I'll just show quickly the results. So we start with nuclear wave packet here, which is excited, photoexcited, and then it just evolves because it's on the sloped part of the surface. And if you look at the dynamics, I'll just have the movie going here. Firstly, the Ehrenfest approximation itself compared to the exact gives very good nuclear dipoles and nuclear densities. And you see that if just looking at the colors, the purple and the yellow clearly have the same trend. These are the linear response calculations, while the green and the red have completely different trend. They curve downwards, and those are the real-time calculations. So again, same kind of dynamics, but done in two different ways. And again, the linear response way of doing it wins out, right? The electronic dipole, there's sort of an underestimation here to do with the character of the state, actually, electronic state. But again, the trend here is much better, and it's not like the real time is any better, actually, here. Okay, so, and I will this just mention very briefly, it has some implications for pump probe spectroscopy. I can talk about that and if you're interested and if you have questions, but I guess I should summarize. So the lack of memory dependence leads to unreliable performance in some cases. If you can somehow extract it from a linear response calculation, even if it's a property of a non-perturbative dynamics, that would be more reliable. Choose linear response Ehrenfest wherever possible. And yeah, just be okay. And then, so actually these two are the main papers, and I will thank the group in particular, Lionel, who is now a former postdoc, he's now a Marie Curie Fellow at École Polytechnique, Davoud, who had done the 3D calculations, Shashoto, who actually just recently joined, and we're very excited to have him in the group to work on both TDDFT as well as exact factorization. He was a former student of Filipp, who is going to speak next, and Evaristo and Patricia, who are working on some exact factorization for non-adiabatic dynamics. And thanks, George, and thank you all for listening.
Thank you very much for giving such an interesting talk. Can I ask if there are any questions? If so, please raise your hand or put them in the chat. Okay, we have a question straight out there on the chat. The Van Fussen work is interesting in the idea of finding a non-perturbative solution using the ionized system's static results. I have an adjacent thought. In theory, a constrained ground state DFT approach using, for example, maximum overlap orthogonality constrained can yield neutral excited states which correspond to double excitations and can capture more full excitation response. Do you have any thoughts on if these meta ground state solutions to constrained DFT can provide a rigorous connection to the real-time density dynamics and or meaningful insights into VXC?
Okay, wow, okay. That's a good question. That's very interesting. So actually just going back to the Van Fussen work, so it's, instead of just to make a small point, it's not the ionized, it's actually the n+1, so it's the anionic, if you like, if anything, right? So, but yes, so constrained DFT, yeah, has been very useful with the ground state, I guess, and yeah, people have looked at like a delta SCF type of approach in some sense, right? I guess is what you're in a generalized way. I mean, these approximations are again, underlying. You're using a ground state approximation for an excited state, right? In some sense, right? Because you're using the same ground state DFT, and in most cases, if the excited state is somehow, a ground state of a certain symmetry, right? Then maybe in principle, right? One can do this. Of course, the functionals should be different, but when it's used for excited state, you're introducing then an additional approximation. So if I understand the question correctly, and so I think then again you'd run into similar problems that we run into with the real time, where we're inputting a sort of a non-ground state density into a ground state approximation, hoping that the exchange correlation effects are the same. So here you'd be saying, oh well, the exchange correlation effects of this excited state should be similar to those in a ground state of that same density, right? So I think maybe you would also have some difficulties there. Sorry, I don't know if that answered the question.
I'll let Duncan respond if he has anything to follow up on. But I just wanted to ask, kind of connected to that, the kind of insight into the kind of these peaks and troughs, these non-adiabatic features in the potential.
Yeah.
Is there any physicality or insight that you can find into them? Because these sorts of very non-smooth features are also found in the exact potential for ground state calculations as well. But I'm just wondering if you have any insight into this kind of non-perturbative regime in time.
Yeah, no, that's an excellent question, and we've been dwelling on this for a while. And Davoud we're trying to finish up sort of a little review paper with Davoud on which will address some of this. So yes, in the ground state case, often these steps are associated with a fractional charge issue or something, or even in ionization it occurs. These steps are very different in the sense that, firstly, so the ground state one, if you had the exact ground state approximation, you capture it, right? If we use that exact ground state approximation here for the time-dependent case, we don't capture that. It doesn't give the same. So the physics is different. And so what is the physics? Well, we find that the step features are related to a sort of local acceleration across the system. And in fact, if we look at this expression for Vs, right, it's not Vxc, so V external is hiding in here too. So we have to be very careful analyzing equations like this. However, we find that if we just simply plot this, plot that, right, we find that the step is appearing from this term. Alpha is related to the phase, which in some sense is related to kind of an acceleration, a local acceleration in the system. So it's a sort of an integral in space of a local acceleration, and this gives a step feature. And these peaks are arising from sort of these velocities in the system. So yeah, it's actually an interesting question, and I think Lionel also was thinking about this, like, well, could we then model an approximation which just just takes sort of accelerations and integrates and do this? And it's difficult again because those terms are also including a V external. And so we'd want to kind of subtract that out somehow as a functional while we're doing this. So it's food for thought, but I don't think it's immediately obvious how to model these. I'd love to know. Yeah, I mean, the more complicated way he was finding these steps in an approximation was through let's see, which is explained in these papers, is coupling it with a density matrix propagation. But that's also numerically much more intensive, let alone unstable after some time. So it wasn't a good solution to the problem. So yeah.
Thank you. Okay, thank you very much. Are there any other questions? Anyone want to stick their hand up? If not, I think we'll thank Neepa again. Thank you very much for a very interesting talk. And I think we'll move on just about on time to our final speaker. So our final speaker is Filipp Furche. If you want to share your slides. Filipp is a professor at the University of California at Irvine. And from a technical point of view, as this is kind of a technical symposium, Filipp's made big contributions in response and derivative theories in lots of different contexts, including to focus on one of them, the random phase approximation, and really its connections to DFT, and making it really a practical tool in quantum chemistry. And so I think he's going to be talking about some of that, but also related to kind of the nature of how excitations can tell us about correlations in the ground state as well. So we're very very happy to have you here, Filipp. Thank you for giving a talk, and take it away. Thank you.
Oh, thank you, George. It's a great honor to speak here in front of this audience, and also after Marc and Neepa. One reason why I picked this subject is that I know that quite a few of you are interested in materials at the Thomas Young Center. And I want to use this as an opportunity to tell you a little bit about our understanding of dispersion interactions and our current understanding, and try to challenge some established notions. It's always fun to do that. So, but I want to begin by acknowledging my group. So this gentleman just last week got his PhD here, and the work that I'm talking about is mostly the work of Brian Wren, who is right here, and Devin Hernandez is an undergraduate student who is in the audience, who's also been vital for this project. Manny Flores is a first-year undergraduate, so all graduate and undergraduate students. Yes, well, let's see how far we get today in the outline. I want to start, just in case we run out of time, I want to start by summarizing the two key results here. So the first result is that really the notion that dispersion is somehow weak in the sense of a small perturbation turns out to be untrue. And I'll try to show that. And the second important result is that there is a property that we call dispersion size consistency. It's a special type of size consistency. And that is actually violated by perturbation theory fundamentally. And that's, we think, part of the deeper reason why these methods do not work for dispersion interactions. And this has been published last year. This work is just under review at the moment. We hope that'll be out soon. So when we talk about dispersion, of course, there is the question always: is there anything new here? Really, I mean, we just think of them as some sort of weak, omnipresent interactions that have this 1/r⁶ power law. There's this picture of somewhat unclear picture of instantaneous dipoles that are interacting, that give rise to these dispersion interactions. And in fact, it is implied in some of these ideas that perturbation theory somehow works for dispersion. For example, that's how you derive the 1/r⁶ power law, right? That we all know from undergraduate classes. So the range of applications is very broad, right? Much broader than one would think, perhaps because it turns out that especially in larger and more sterically crowded systems, like transition states or biological systems where you have a lot of non-covalent interactions, these dispersion components in the interaction energy are quite important. And of course, the same is true for supramolecular chemistry and things like nanocrystals or so, right? And I know that there's ongoing research in your center as well on all of these topics. So let's start with looking at some benchmark results. Here are sort of the technical details. I want to emphasize that it's really, really important when you do correlate wave function calculations, any type, including RPA or coupled cluster, to do complete basis set extrapolations. You cannot just do a triple zeta calculation and hope you're there. It's just not true, okay? And you have to really make sure that everything is converged. I also want to point out that all of the calculations that I'll show you are done with Turbomole. Turbomole is now has now restarted to distribute licenses on our own. So if you want to get an inexpensive no support license, you can always do that, directly get that from our website. But let's take a look at the results now. So a particularly nice benchmark for dispersion interactions is this S30L benchmark by Grimmett. It's about 10 years old, and it's L stands for large. So these are systems with up to 200 atoms. And they're all non-covalently bound. Some of them try to mimic, different classes of dispersion interactions. Some are more hydrogen bonded, others are sort of purely dispersion, like these blocky catchers here. And so, we've just thrown various standard quantum chemical methods, or in fact, Brian has done this. I've just thrown them at this benchmark. And the first really, so here's the number of the complex, and here's the error in the binding energy relative to PNO CCSD Francis T. And we know that these numbers are probably accurate to about 1 kcal per mole, because there's also relatively good experimental data. So perhaps one of the most surprising results here for us was that the error for MP2 is actually huge. Okay, so especially for those bucket catcher systems here, but also for some of the other ones, 9, 10, 11, 12, right? So 9, 10, 11, 12 are those with the fullerenes, but even here there is some, or here 25, 26, that have some aromatic systems, conjugated pi systems. You have huge errors in the binding energy. Keep in mind, typical binding energy here for these complexes is on the order of 10 to 20 kcal per mole, right? So these are errors that in some cases exceed 100% in the binding energy. So disastrous, catastrophic errors. And of course, that goes entirely against the notion that perturbation theory should work here, right? I mean, it really doesn't at all. And so you don't see this in the smaller benchmarks, right? If you look at S66, for example, or even the L7, which contains a few larger systems, you have mostly relatively small errors. Although you see a little bit already cropping up here in L7, but it really gets shockingly large when you go to the S30L benchmark. And what you also see here is that RPA really stays quite nicely constant, relatively constant over the whole benchmark set. In fact, this is even on a relative scale a little more accurate than what you get for the smaller systems. And the dispersion corrected DFT methods here, the D3 and D4 methods, they actually also are pretty good, although they have somewhat larger outliers for these larger systems. So okay, well, what's the origin of this? The first question, first idea that comes to mind, of course, well, maybe there's something with small gap systems going on. These are perhaps bad Hartree Fock cases. So we've plotted the correlation of the error with the HOMO-LUMO gap in electron volts here, and this is really the Hartree Fock gap to be consistent. And you see here is a fairly large scatter, and you also see that the gap doesn't get all that small, right? So really, there is not a good correlation here that would immediately tell you, okay, well, these systems are becoming metallic or something, and therefore you would expect perturbation theory to break down. It's not true. So this can't be the cause, at least certainly not the only cause. And then we look at system size, and here it gets more interesting. So if you count the number of valence electrons and try to correlate it with the error, with the percentage error, this is the relative error, not the absolute error, of course, right? The percentage error, which we would always hope to be more or less constant, right, with our quantum chemical methods. You see that, well, for the dispersion corrected PBE and also for RPA, you're actually quite constant here, but for MP2, and to a lesser degree for some of the SCS MP2 variants, the scale MP2 variants. Unfortunately, there is this linear increase of the relative error at a rate of around 0.1% per valence electron. Okay. And, you know, when I saw this, I could not understand it because my sort of conventional quantum chemistry education is MP2 is size consistent, right? Or at least size extensive. And so we'll get back to that later. So to analyze this more, a very convenient framework is the adiabatic connection fluctuation dissipation theorem framework. And so I think Marc mentioned a little bit about this in his talk before, but I just want to remind you, we have a Hamiltonian, and so what we've done here actually is we have sort of adapted this framework specifically to van der Waals interactions. So so this is a special case, and it's really neat because it actually exactifies the symmetry adapted perturbation theory in a sense that I'll show you in a minute. So we look at this AB complex in the large interaction limit. So there's no interaction here. There is no overlap here. There is interaction, but there is no overlap between the subsystems. And we scale, instead of the whole Coulomb interaction, we scale only the interaction between the two fragments. That's the crucial difference compared to the standard adiabatic connection method, all right? And then we introduce this coupling strength dependent Cohen-Sham potential that fixes the density, okay? So that makes our ground state density equal the ground state density of the interacting complex for all alpha. But we've only density functionalized the part of the interaction that really comes from the interaction between the dimers. The intramonomer interaction is at full coupling. So if you turn off the interaction here, you don't get the conventional Cohen-Sham system. You get the monomers with an additional local potential that forces the monomers without interactions to have the dimer density. And this is particularly useful for analyzing van der Waals interactions, as we will see. So now everything that, you know, so now everything that's not electron interaction is packed into this alpha dependent one body potential. And we can write the interaction energy only as a coupling strength integral that involves only the potential energy of the electron-electron interaction. And one thing that's really nice about this theory is that because of the density constraint, you get rid of all the induction terms. So automatically, everything that's beyond first order in the coupling strength in this interaction energy turns out to be dispersion. There's no induction terms, which is great. And you can do an analogous formalism for the Hartree-Fock reference actually, but I'm not going to talk about this in more detail here. So now by invoking the 0-point fluctuation dissipation theorem, as we do it for the standard adiabatic connection formalism as well, we can express the correlation energy in terms of the polarization propagator of the non-interacting monomer system. And again, keep in mind, non-interacting doesn't mean Cohen-Sham, it just means the monomer by itself at full intramonomer coupling, but with the density of the dimer. All right, so that's the pi naught here. And we have a exchange correlation kernel. We just heard from Neepa about that in her talk a little bit. We have a Hartree exchange correlation kernel here, coupling strength dependent. But again, it's only for the inter-monomer interaction, right? At imaginary frequency. And then there is this screening factor, which is actually also expressible in terms of the kernel. And that is just basically it's a sort of second order dielectric function here. In the case, it turns out it only is second order in the case of the dimer. That takes into account screening effect. So if you nix this kappa here and you only take k alpha to first order, you get back to your you know, longitude in ceramic cone, second order dispersion energy that you know from perhaps from an advanced textbook, right? And which has the 1 over r to the 6, C6 over r to the 6 as an extreme asymptotic limit. But this is actually, this can be exact when you, at least when you had the formally the exact hard to exchange correlation kernel here. This gives you the exact dispersion energy between the monomers up to exponential accuracy, okay, which is really great. And this really allows us to sort of, you know, formalize the dispersion, the calculation of the dispersion energy a little bit and discuss some nice formal properties here, right? So we can write this diagrammatically as the interaction between these two monomer polarization propagators, which are sort of particle hole propagators, right, that you see here for the monomers. But unlike in the normal many-body perturbation theory that you might be familiar with, or maybe many-body Green's function methods you're familiar with, unlike in those approaches, we have the fully intra-monomer interacting monomer polarization propagators here, as indicated by this blue filling, right? And then the interaction is the screen Coulomb interaction that we just saw here before, kappa to the -1 times V int. That's the screen Coulomb interaction between the two subsystems, and then the other one is the kernel, right? That's the one we see here, okay? And so this is a quasi-second order picture that is, however, exact, okay? And we can now go back and sort of re-expand this and then see what happens in the limit of small alpha, where we recover the perturbation theory. One really nice thing is we can actually derive an upper bound for the convergence radius of this expansion, simply by noting that this is a geometric series here, this kappa expansion, because kappa is, you know, 1 minus something, right? And we can estimate the magnitude of this something and derive an upper bound for the convergent radius, where we basically just use the fact that the geometric series converges within a circle of radius 1, right, within the unit circle in the complex plane, okay? And so that's our convergence criterion, and that gives us a really nice way to analyze various methods now, right? And so in RPA, we just replace the kernel by the Baire interaction, the Baire Coulomb interaction, and we use the RPA for the monomer polarization propagator. And this gives us this expression for the dispersion energy. We can integrate this and we get this logarithm of the inverse screening constant. And this is great because now we see immediately, as long as, you know, the norm of kappa stays below 1, we can expand this in a Taylor series around kappa equals 1, right? Because we know that the ln is analytical in the complex plane, but it has singularity, well, except for the origin, where it has an essential singularity, right? And so as long as you stay away from that, you get a convergent Taylor series. And in case of RPA, this turns to be always satisfied unless you have these Dobson-Gold conditions where kappa becomes singular. And to have that, you have to have a system that's macroscopic in at least one dimension, but finite in at least one other dimension. So think of two metallic nanowires attracting each other, right? You must have infinite wavelength density fluctuations, okay? So some kind of Goldstone modes, and you need to have a zero gap. If these conditions are satisfied, then indeed also, then we actually believe that there is no perturbation expansion, and that's what gives rise to these odd power laws that Dobson discovered about 10 years ago, right? So, so there can be a situation where perturbation theory doesn't converge for physical reasons, and that is reflected here. But there are many other situations where this is not the case. For most molecules, this is not satisfied, certainly not for the ones that I showed you before. And for those systems, the perturbation series should converge, and RPA tells us that it does, right? So what's going wrong here? Well, if you look at MP2, the thing that's going wrong is that actually the problem is with the treatment of the monomer. In the case of MP2, you're basically replacing the monomer polarization propagator, the interacting monomer polarization propagator, with the non-interacting Hartree-Fock polarization propagator. And that turns out to be unbounded, okay, as opposed to the RPA one, which is bounded by one, right? And so that's the origin of the divergence of the perturbation theory mathematically speaking in the systems that I've shown you, right? And so just to summarize this here diagrammatically again, so here we have the RPA, which is very similar to the exact case, except that we're not using the exact kernel, we're just using the first order approximation to the kernel. Here we have this thing called MP2C, which some people like to use, which is sort of a partially screened perturbation theory, where you basically just do away with this screening factor, but you're still using the screened monomer polarization propagators, which is a smart thing to do based on what we just discussed. And then you have MP2, and there you have the non-interacting monomer polarization propagator, and that breaks it, right? And so you see this when you plot the errors versus the errors in the energy versus the convergence radius. So this is the PBE computed convergence radius. So you get a little bit more than a factor 2 in sort of error, in sort of margin before it really explodes. But once you exceed sort of 2 or 3 in 1 over alpha, you know, the errors are all over the place, right? And you can also then compute term by term explicitly the perturbation series, at least within RPA, which we've done here, which Brian has done. And you see that, you know, the first orders, it's still pretty well behaved. And then for pretty much every single system that we have studied, except for helium dimer, where the convergence radius is actually below 1 or close to 1, you end up with divergence. Okay. So same thing here, even for water dimer, which was actually believed in older work to be a prototypical case where perturbation theory works for dispersion. It turns out you have to go beyond n equals 10 to see the series converge. So you know, the lower orders are still fairly good, but of course it's not particularly trustworthy if you're calculating the low orders of a divergent series, right? And you see here again that the size dependence actually for the convergence radius doesn't matter all that much, although it gets a little worse. But once you have exceeded even just a few atoms, this is helium dimer here, and for everything else pretty much, you're already beyond 1. And so the physical picture here is simply that in MP2, you're just having the you know, the unscreened polarization propagator for the monomer. So what this means is that if you have a dispersion dipole, right, that dispersion dipole in the monomers cannot induce other little screening dipoles that sort of attenuate the interaction between the two. And that's why the interaction becomes long range and too strong to be tractable by perturbation theory, right? And so this is, physically speaking, the reason. And you can now, you know, go along and try to, this is just sort of an extra slide I wanted to give to you to show you that you can actually compute these actual collective density modes that underlie those fluctuations that give rise to the van der Waals interaction in a sort of way, in a natural, what we call natural plasmon decomposition. So these 10 plasmon modes here give you actually the 90% of the ground state correlation energy of the silver 20 cluster. And you know, they're not really excitations in real time. There's something like, you know, collective density fluctuations that have maximum contribution to the correlation energy, but they still can tell you and quantify actually the modes that give rise to the largest contribution to the correlation energy. And now there is this other concept as well, where we looked at a larger system with many monomers, n-monomer system. And we can actually then show that at large but finite distance, the dispersion energy of a subsystem that you take out of these, so let's say we cut here, right, the two lower rows, and then you just take the interaction between the three lower rows and the first one on the top row, we know that the dispersion energy of that composite system must be equal to the dispersion interaction of the dispersion energy of the K-mer, so the three lower rows within themselves, plus the interaction between that and this extra one. Now that seems trivial, right? But it isn't. It actually really is not trivial when you try to see what various methods such as MP2 do here. And a little more elegant statement of this dispersion size consistency is that the total dispersion energy of this whole thing should be completely independent of any partitioning into any subsystem. So however you cut, you should always get the same dispersion energy. And that's of course kind of intuitive as well, but it's highly non-trivial, and it's actually a very strong statement for an interacting system at finite distance. Usually in the textbooks, you only talk about infinite separation. You talk about finite separation of an interacting system here. Pretty strong statement of size consistency, right? And so that's the difference also. That, you know, MP2 is still size consistent in the extreme limit of complete non-interacting system, but at finite separation, no longer size consistent, right? So, you know, I'm not going to talk much about, because I'm also running out of time, but I'm not going to talk much about how this is proved, but I just want to mention that one way to prove it is to do a multivariate extension of this adiabatic connection approach that I just discussed with you before, where we now have a coupling constant for each monomer pair, right? And so our coupling constant becomes a matrix, coupling constant matrix. We can do the same fluctuation dissipation theorem approach that I've discussed before, except now we have a path integral over this n times n minus 1 dimensional coupling strength space. And the nice thing now is that you can then argue, you can show that, of course, the final result is independent of the path, okay? Because it turns out this is a total differential, right? And so what this corresponds to is what I just showed you here. It doesn't matter how you partition it and which interactions you first switch on, and then which actions you switch on second, and so on. Doesn't matter. You always get the same result because it's path independent, right? And so then this means that you get separability, you get multiplicative separability of your screening factors, which is not satisfied in perturbation theory, but it is satisfied in RPA. And you get an additive separability in the correlation energy. And again, so, you know, let me just say this as the last thing, perhaps. In perturbation theory, if you want your total integrand to be first order, you already get a factor alpha from your interaction, V alpha. And so if you expand in MP2 your screening factors of your monomers to first order, it turns out, if you wanted to get a dispersion consistent interaction of a compound system, you would need to go to fourth order in the energy in order to have first order accuracy in the monomer in the monomer polarization propagators. And that's the crux. It's very, very similar to the problem that you see with size consistency in CI methods in beryllium dimer, except that here we're talking about here we're really talking about these dispersion interaction dipoles. Okay, so is this relevant? Yes, we think so. And I just want to show you this as a one last slide on application. So this is a transition state for a radical controlled reaction. My former postdoc, Mikko, who is now working at Janssen Pharmaceuticals and was at BASF before, has really used this to design a new catalyst for this polyurethane synthesis, which is it's a million ton chemical industry synthesis per year, which is hugely important. I mean, these things are everywhere in our clothes and our houses and stuff like that. And what he was able to do using these RPA calculations, not MP2, but you really need to use RPA here to get the transition state right, was optimize a completely non-covalent catalyst for this polyurethane polymerization synthesis. It really does away with most of the unwanted side products. Okay, so the two really most important conclusions is stay away from perturbation theory when you try to do dispersion interaction in larger systems, materials and things like that. It's not a good idea, right? And the reason really is that it diverges and it's not size consistent, despite, contrary to what we have learned or what we might think, it's not size consistent for dispersion. And RPA really is a much better alternative there. It's not more expensive, essentially no more expensive than MP2, but it gives you dispersion size consistency. And especially, if you're doing something like a nanocrystal or so, or even molecular crystals with smaller monomers, I really think that going to something like RPA is needed. Thank you. That's it. That's all I had to say.
Thank you very much, Filipp. Very interesting and I guess important talk. I mean, I guess Phil Anderson was right when he said more is different. And I guess this reflects that. I mean, you often see actually in papers, comments like if you want to go to larger systems, you need an infinite resummation of diagrams, I guess without citation. And, this kind of codifies that in some sense and makes it quite explicit, which is nice to see.
I think that's right. And I think, there's also differences. I think the solid state community might have embodied this a little, got this a little sooner. But, in quantum chemistry, people still stick to their perturbation theory a lot.
Yeah. I mean, I guess you never do bare perturbation theory in the solid state. Traditionally, you always start from a, because I guess from their experience with the uniform electron gas, I suppose, where it's all essentially plasmon driven in the high density regime. Okay, are there any questions? If you want to stick them in the chat or put your hand up. Just to kick things off while we're waiting, I just thought I'd ask a question about, you did have results on sort of SCS and SOS MP2. They always sit a little bit uncomfortably with me as methods, but I was wondering whether this sort of analysis could say anything about those sorts of methods at all. They did look as though they were size extensive in terms of capturing some semblance then of many body dispersion interactions. Is that yes, reasonable to say, or is there something you can say about the radius of convergence of the perturbation theory in this respect? Or
right, yeah. So I mean, what happens with these SCS methods is that they do a little better because you're scaling down some of the most problematic terms in the MP2, and of course then you also have some there's some additional, I mean, depending on which version you use, you also have additional fudge factors in the zero order solution, right? But I mean, there is a slight slope here, right? So they're fundamentally not dispersion size consistent, and they can't be. But again, you just sort of get away with them for a while because you're sort of absorbing some of the worst errors in this empirical correction, right? And I think the same is true for, you know, the D3 and also D4 methods. Fundamentally speaking, those will reach their limit. And I think it's known that in some, you know, in some solid state applications, they don't do particularly well. You know, if you try to apply them to something like solid coinage metals or something, I think people have found larger errors. But for everything that, you know, you can still do in a quantum chemical calculation, at least nowadays, with molecules, they still seem to be okay-ish, yes. But I would not apply them to anything that, you know, has a smaller gap or is really highly polarizable, or even, you know, I even think it gets problematic in the bulk limit. Yeah.
Okay, thanks. Okay, Patrick has his hand up.
Yeah, thanks, Filipp, for this great insight. It's really interesting. So what's your opinion when you move away? So presumably your analysis also to some degree holds true for covalently bonded systems, right? When you move away from dispersion interaction. But then it's clear also that one has to go beyond RPA in many cases, right? Really for chemical accuracy. So what's your opinion then on how to go beyond RPA? Because this has been a bit of a problem. So I guess the same principle has to hold true, right? That you can't do it with a simple perturbation. It has to be two all order perturbations, right? So let me clarify this first, right? I mean, this is a particularly good case for RPA here because we're in this asymptotic limit where all the exchange interactions are basically zero by definition, right? So as you're certainly aware, right, the largest correction to and the largest problem of RPA at finite distance is that it doesn't, at least the bare RPA that we're using here, does not include exchange, right? And so you get this much too negative pair correlation function at the origin. And so you need some kind, at least physically speaking, you need a local field correction of some sort. Now, I think that, however, you know, if you, and so, I mean, we've looked at, in 2018, we've looked together with my student Gore, we've looked at the convergence of RPA renormalized perturbation theories. And it turns out it's a lot more benign than this MP2 perturbation theory, because you start from an already screened reference, right? So while I agree with you, and we have found cases where RPA renormalized perturbation theory diverges as well, right? But you really have more of a error margin. Ultimately, I think you're right, though, and you know, I think the use of perturbation theory for these relatively strong Coulomb interactions is just, in some ways, is fundamentally flawed, right? I think that's sort of my strong feeling here. Yeah, and we're just doing it because we don't have anything better, right? But it's not really the right approach for these unbounded, you know, Coulomb interactions. Yeah. Thank you.
Thank you.
Thanks. Okay, Neepa, you had your hand up briefly. It then went down. Do you have a question?
Yeah, I had a question, but if there's time, maybe. But
sure, we'll make it the last one.
Oh, okay. So thank you. Yeah, no, beautiful talk, Filipp. So a quick question: in your perturbation theory, did you say that your propagators and so on are evaluated on the monomer density or on the dimer density, and how important is that? Like when you take the pi zero, because
that's a good point. So in this perturbation theory, we have to use the dimer density, right? So we always have to use the dimer density, and that's easy to do when you do a supersystem calculation, right? That's what you do anyways with a supersystem calculation. But if you wanted to implement this in an SAPT fashion, right, which is a lot more, in some sense, is a lot more appealing, then you would have to first do, if you really wanted to do this right and get rid of all the induction terms, you would have to first do a Kohn-Sham calculation for the dimer at large but finite system at a distance with the interaction turned off and this Kohn-Sham potential turned on, right? So you always need to use the dimer density here. If you don't use the dimer density, then you get the additional induction terms, which we know from conventional SIPT and such can be they can be non-negligible, although it is believed that in most large systems the dispersion interacted aren't two polar. It's believed that dispersion often dominates induction, but you have to, if you want to get rid of those, you have to use the dimer density, absolutely.
Yeah. Okay, thanks. Thank you.
Thank you.
Excellent. Well, we're pretty much bang on time. And I just want to thank again the 3 speakers from this little mini symposium who all gave excellent talks. I thought it was a fantastically interesting set of talks. So thank you very much from myself and the TYC. And I really hope that at some point we can all meet up in person. So thank you very much, and we'll end the symposium there.
Thank you for organizing.